effort in having these sessions every year. It's really fantastic, and it's nice to meet all these people every year. It's really a good occasion. So thank you very much, and thank you very much for inviting me. It's a pleasure. So when discussing about the topic of the talk, I asked to Giulio what he wanted me to speak about. And there were two options. One was a result that I obtained with Guglielmo about the LE partition functions of certain classes of 6D2,0 theories. And the other option was something about non-invertible symmetries. And so we decided for this, but of course, if you're interested in the other, I'm around, so we can also talk about that. So this is a joint project together with my PhD student, Elias Riedel-Gorning, and he's approaching his final year, so very, very strong student, and my postdoc, Azim Hasan, whom also is based in Uppsala, working with me since about 3 years, and will move back to Pakistan in September. Yes, I will speak about some aspects of non-invertible symmetries in 3+1 dimensions, focusing on some application to dynamics, specifically the notion of symmetry-enforced gaplessness and the spontaneous breaking. And since I'm sure this is not an audience of experts about this topic, I will start slowly, so apologies for the expert in the audience. This will be a slow start, but hopefully you will find the end of the talk interesting anyways. So there is an increasing amount of evidence that indicates that the symmetries of quantum field theories are encoded in topological defects. And this started more or less 10 years ago with this work by Gaiotto, Kapustin, Seiberg, and Willett about Heiger P-form symmetries. No? And which in particular gave conserved quantum numbers to extended operators and allow it to restate various results about the dynamics of quantum field theories in terms of aspects of those symmetries. For instance, confinement can be explained exploiting the breaking of one form symmetry. And but then it can be generalized further. No? So it has a further generalization. And the further generalization consists in promoting any topological defect in the quantum field theory to a potential symmetry generator. No? And these topological defects will act on operators in various ways. They can act on them by linking them. So you can consider inserting an operator at a given point, for instance, and wrapping it by a topological surface. This surface shrinks, and you obtain a new operator. And this generalizes to lines, so you can link lines or extended operators by topological defects and obtain new ones, no, by shrinking the corresponding linking defect. Of course, you can also have actions by crossing, so you can have a topological surface, take an extended defect, it crosses it at a given point, and it gets transformed. No? So there are linking and crossing actions. And so this is, in a sense, the way in which one extends the action of symmetries to the action of topological defects on other defects that are non-topological. So on the blackboard, the ones that are drawn in red, in pinkish, are non-topological, and the white ones are the topological ones. No? Now, the point is that the topological defects, they can form junctions on their own, and these junctions are structures that for ordinary symmetries, which are labeled by group elements, encode the group law, the group multiplication. for generalized symmetries, one drops the group multiplication and one can have more complicated structures, where here one has multiple fusion channels. No? So that's one feature of topological defects that extends the notion of symmetry, that they have a group law is replaced by a fusion product. And then on top of that, one also have the possibility of forming junctions of higher codimensions. So yeah, we see that the two form a junction in codimension 1, but if you bring 3, you can see that they can form higher and higher codimensions. No? I won't draw it on the board, but you can imagine. Okay. So this kind of structure is give to topological defects a higher structure. So this structure is typically represented by a symmetry category that replaces the notion of a group, where the morphisms in the category are just parameterized by these interfaces. Okay. And higher codimension interfaces give rise to higher morphism in this category. So there is this relation. No? But Giulio asked to not go into the mathematical details of this. I give a physics-oriented talk, so I stop about the higher category now. If you are interested, I can say more in the question session or afterwards. However, what I want to say is that the existence of these non-invertible symmetries is well known. So in 2 dimensions, we know that they exist since a long time. No, so they are well known in 2 dimensions. And like a paper that formalizes them very nicely is a paper about that has topological defect lines in the title. Topological defect lines. More or less, it was 2018 something, and I think it was Xiao and other Xiyin, Xiao, and Yifan Wang, and I shouldn't have started this. And Xiying at the time had a lot of students, and all of them were involved in this project. So I apologize if I have forgotten the name of some. But the point that I wanted to make is that these are well known in 2 dimensions, and they have a well-known consequence. So an example that I want to discuss that will be relevant for what follows is the Kramers-Vanier duality. So Kramers-Vanier duality defects, they have been realized for the first time in the context of the critical 2-dimensionalizing model. And they have the following structure. So the 2-dimensionalizing model has a Z2 symmetry, and so it has a Z2 symmetry. But at the critical point, it develops an interface that take order operator into disorder ones. So this will be sigma, this will be mu. And like this line carries a composition of the generators of this Z2 symmetry. No? And this has been then generalized to structures that are called Tambara-Yamagami. Which are labeled by a group, G, in this case it would be G2, and a line like this, that has the property that fusing the line against itself give rise to the sum over all the elements in the group. Okay, so you can see that this implies this rule, because if you take this operator and you move it across this interface, 1 second. No? The fact that n squared give rise to the sum of the elements in the group is exactly what you need to produce this relation. Yes? Mm-hmm. Mm-hmm. I think that I can. Is it okay if I tell about the partition function? We can also probably derive correlators afterwards. The idea is that you can often nucleate a bubble of this topological defect at the price of a normalization factor, and by moving around the bubble on the Riemann surface that you are interested in, you can produce non-trivial relation by folding the defect on itself, exploiting the topology of the surface. No? So maybe as an example, let's consider this case, this one, and let's study the case of the so the other operations are so n can absorb the anything, and this one is equal to just n, and then the LGs, they will just fuse according to the group law. No? So this is probably one of the simplest examples of a symmetry category. So to address Alba's question, let us see what this implies for the torus partition function, for example. No? So you consider just any two-dimensional theory that has a collection of lines that satisfies this algebra. Okay, so this one. So there are elements in the group, and there is another line that has this property. Okay, this is all we know about this theory, nothing more. No, so let's consider, for instance, the torus partition function. No, so I draw the torus in the usual way. We identify the sides. Okay. So now this one we can at the price of inserting a normalization factor, if necessary. No? We can rewrite as follows, no? We just bubble this line out of nothing on a circle, no? Like this. Okay? Now, we can exploit the topology, no? So we can, for instance, move this line up this way, hit the corner, no? When we hit, we can move it around because it's topological. So if we don't hit any insertion of local operators, we don't change the value of the partition function, no? So we move it up. We go up here to the corner. So now we have one line this way, one line this way, one line this way, and one line this way. Okay? It's still the same circle. I just moved it up, and then using the identifications, I have an S1. Okay? But now we can exploit this topology to highlight the fusion rule. No? So we can squeeze these lines together. No? And what we obtain? Then something that does like this. No? Still a circle, but now we can bring these two arbitrarily close. No? So let me continue up here. And I forgot the factor. So now, let me change color. See that here, I can use the fusion rule in this direction. So here I have a plus over G of LG. And then I can use the fusion rule in the other direction here. Sorry. I get a plus over, say, G prime of LG prime. Okay, I just used this relation on this line and this line. Okay, and I end up with a circle. Sorry, I draw it in the wrong place. I draw it here. I wanted to draw it there. But okay, so now we know how to derive the first figure. So we have this, and now we can shrink this down to 0 size, no? At the price of paying the normalization factor. And we obtain just a collection of lines here, and a collection of lines there. But now you see, like, this was the partition function on the torus of the theory T. And this one is exactly the partition function on the torus of the theory T, where we have gauged the symmetry G. No? Because gauging a finite symmetry is equivalent to summing over all possible ways of decorating a simplicial decomposition of the manifold. And in the case of the torus, there are only the A and B cycles that we have to decorate. And these sums are exactly doing that. These are the decorating the two cycles of the torus by all possible backgrounds for the G, for this G symmetry. No? So, out of the existence of this non-invertible algebra, we have established an equivalence of partition functions. No? So that's why they are called duality defects, no? Because they are an expression of the duality between the theory with the group gauged and the theory with the group not gauged. Yes. This happens at critical temperature, yes. Good question. Good question. There are probably like approximations, no, in which you can treat this. If it is mildly broken, you can probably still see it. If not, not. Like it's. I mean, the symmetry is realized exactly only at the critical point, no. Yes.
What is theory, for example, on a finite elevator, so only in the scaling limit?
It is possible to realize this also on the lattice. So you can do it on the lattice.
Even on the finite.
Yes, there is a way of doing that. We discuss it in detail, if you are interested, in a review that I wrote together with Ingo Runkel and Niels Karkeville in last year. So it's a nice exercise. It wasn't it's non-trivial, but and I think that the first one that did it on the lattice were Assem, Fenley, and somebody else. Again, I'm really bad with references, but yes, so it's possible to do it. Yes. High temperature, low temperature. Yes, it's like a duality, no? But yes. So you, I mean, but you can still like maybe do a spurion analysis. I don't know, like in the but yeah, it's broken explicitly, yes, because it maps it's like yes, indeed, as Andrea mentioned, no, it maps to different theories. Yes. Yes. It would become an interface between a theory at high temperature and a theory at low temperature. Yes, thank you.
Going back to the question of lambda, but in the end, I mean, you also want to check the partition function with the massive.
Mm-hmm. Yes. Yes, these are all computations, but computations that probably have been done already in the context of two-dimensional theories in the past. No? But the point is like so already in two dimensions we know that they exist, but we know that in two dimensions there are many funny things happening. No? So maybe these were a property, this non-invertible symmetry were a property only of two-dimensional theories. But they are not. No? So this is a more recent result that was obtained a couple of years ago. No? So about 2 years ago, there are KW-like duality defects in 3+1 dimensions. No? And so this was a result by I think Omori, Kaidi, Omori, and Zheng, and also Cordova, Xiao, Xin, Lam, and Xiao, simultaneously. No? So the way in which they construct them is essentially the same. No? They start from a given theory, and they construct an interface between this theory and and a cousin, and they use a duality. So in 4 dimensions, you see, like in 2 dimensions, what is the idea? The idea is that whenever you gauge a symmetry, no, if you gauge a p-form symmetry in d dimensions, the outcome is a d minus p plus 2 symmetry in d dimensions, no? So gauging finite symmetries always produces a new symmetry. You know, whenever you gauge one, you get a dual one back. No? And so you see that in 2 dimensions, if you consider zero-form symmetries are mapped into zero-form symmetries. And so it's possible that just gauging a symmetry, you get the same symmetry back. No? And in 4 dimensions, the same role is played by one-form symmetry, so symmetries that are charging lines. No? And indeed, this is the idea. So in this case, you start with a theory that has a given G1 form symmetry that is gaugeable. You gauge it, and after you have gauged it, you exhibit a duality with the original theory. No? Of course, one can try to construct generalizations of this structure by gauging in 3 dimensions and in 5 dimensions. And I think in the original paper by Kaidi Omori and Teng, they discuss a mechanism of how to build duality defects in 3 dimensions. It was recently generalized in a paper by Babak in full-fledged. One can do the same thing in 5 dimensions, for instance, and construct duality defects in 5 dimensions using these tricks. So examples of this type, well, one can construct many examples using Maxwell theory. Let's see, how am I doing with time? Oh, it's okay. So you can construct many examples using Maxwell theory. So Maxwell theory has a U1 electric one-form symmetry and a U1 magnetic. And you can consider gauging subgroups here. No? For instance, if you gauge an electric subgroup of the one-form symmetry of Maxwell theory, that has the same effect as shifting decoupling to a multiple of decoupling. That is because gauging a one-form symmetry just changes the quantization condition on the fluxes. And so that's essentially equivalent to just rescaling the coupling by an integer. And then in Maxwell theory, we know that there is electromagnetic duality. So that's a quantum symmetry of the theory, and the quantum symmetry is mapping the coupling to pi over the coupling. No? And so composing, like performing the gauging of this one-form symmetry over half space, and then using electromagnetic duality on Maxwell theory, one can find out that, for instance, at coupling that are like square root of 2 pi over n, no? N times E, so if we choose couplings of this form, they will have families of duality defects of this type in Maxwell theory. So just the special values of the coupling, the symmetry enhances, no? And the duality becomes a symmetry, no? And similarly, one can do, if one wants more interesting examples, it's relatively straightforward to use classes theories. We have heard about classes theories. I think for this audience, I don't need to introduce what they are, more or less. But the idea is that they are theories corresponding to compactification of 6D to 0 CFTs on Riemann surfaces, no? And in this case, we choose a Riemann surface such that it doesn't have any puncture, so that the mapping class group becomes really the duality symmetry. And one wants to just consider fixed points of the mapping class group, no? They would become special points where you tune the various couplings of your classes theory such that they are mapped back to itself by the duality, and they give rise to generalizations of this idea of the duality defect. No? So, like in particular, using class S examples, one could extend. So the examples that were studied by Kaidi, Omori, and Zeng, and Cordova, and others, they always involve Z4 duality groups, like the S duality or a triality. No? and one can extend and obtain more general symmetries. For instance, I know, using the Boltzmann surface. It's a special Riemann surface that exists at genus 2. No, one can find a family of duality defects of non-abelian families. That are parameterized by GL2 of F3. So this would be the general linear group of 2x2 matrices with values in this field. No, this is an example. Just it's a complicated group. It has 46 generators. No, it's not. And using class S techniques, one can also study the fusion of these. So. In particular, there was a work by Antinucci, Coppetti, Galati. And Rizzi, where this was studied in detail. No? So then, well, there is a natural question. No? So we have examples in 4 dimensions. We have essentially as many examples as you want. You start with classes theory. You can produce any. You choose, when I spoke about this to Sergio Ceccotti, he said, well, but you can build any group you want. So he explained how you can realize. This is an idea that he explained to me, how to realize any group you want as a duality, as a parameter for non-invertible duality defects. I think so, like any group you want. But the problem is that in that context you will need a very, very complicated theory, no? Because the construction involves gluing together pieces of the ultraviolet curve of the classes theory, one per generator of the group. In that case, it would be like a monster theory. But so a natural question in this context then is about the interplay of these non-invertible symmetries. So interplay with dynamics. So in particular, we're interested in RG flows. No, we start from a theory, the UV. We go to a theory in the IR. No, is there gapped or gapless? And in this context, we start. If we would like to start with a UV theory that has a KW like a non-invertible symmetry. And we want to study an RG flow which is triggered by a relevant deformation that is symmetry preserving. No? So and now, like, well, these are non-invertible. They are more general. They are represented by topological defect, but they really behave as ordinary symmetries in this respect. No. So what one could obtain, like, various possibilities. One could have an infrared which is trivially gapped, and symmetry preserving. One can have an infrared which is some sort, again, symmetry preserving. Well, maybe, yes, and some non-trivial topological order. One can have a gapless infrared, which is symmetry preserving. Or one can have spontaneous symmetry breaking. And in this case, it can be either gapped or gapless, and there are various combinations. No? So we would like to say something about this, like assume that you have an invertible symmetry of the Kramers-Vanier type, and like an RG preserving RG flow, like a symmetry preserving RG flow, what can we say about this? No? And there was an interesting result in this context. Were obtained by Aguilera Damià, and then Argurio, Benini, Benvenuti, Coppetti, and Tizzano earlier last year. I think it was in May last year. No? They studied in particular deformations from n equal to 4 down to n equal to 1 star that were symmetry preserving. No? The mass deformations of n equal to 4 that are compatible with the action of the duality symmetry. No? And they have an interesting result. In fact, they can explain they explain the structure of vacua for n equal to 1 star in terms of the spontaneous breaking of these KW-like symmetries. There are interesting implications. No? Moreover, this also led to insights on the structures of anomalies, which were obtained shortly after by people in this audience, as well as Sun and Zheng and Cordova, Sin and Zheng. No? And this collection of the results was the starting point for Elias, me, and Azim when we started looking at this problem. So there were this construction. We have obtained, like with Azim and Vladimir Bashmakov, these results about classes theories, these infinite families of examples, and people had started looking at possible implications to dynamics. So is there something that we can say, like, is there something more that we can say, or something more systematic that we can say about this? No? And there is a new ingredient where, again, more or less developed in the same period. These are very recent developments. A new ingredient is the so-called symmetry TFT. Well, new. It was all known to experts, let's say. No? So you can read about the symmetry TFT in papers by Seiberg and Kapustin written before the paper about generalized global symmetry, but this has been systematized very recently. And exploiting the symmetry TFT, one can say, like, one can streamline the construction of duality defects. And one also has a machine that one can use to try to tackle this type of questions. No? So how would one use the symmetry TFT to build a duality defect? No? How can we go about it? No? So let's do it in d dimensions. So you start with a quantum field theory in d dimensions. And the whole idea is that, like, this is a quantum field theory in d dimensions, so it assigns a number, its partition function to a d-dimensional space. And you can realize your theory of choice. Let's call it TV. Exploiting an isomorphism that involves 4 pieces. Okay. So we have a relative field theory, a relative d-dimensional field theory here. Let's call it T hat. No? This theory is relative to a d+1 dimensional bulk topological field theory. Let's call it F. And here we have a choice of a d-dimensional gapped boundary condition for F. So what is a relative field theory? No? A relative field theory is a complicated name for a bulk boundary system. Okay, is a quantum field theory that lives on the edge of another one. Nothing more than that. No? And for this reason, like instead of assigning to a closed manifold a given number, it assigns to it a vector in the Hilbert space of the bulk field theory. No? Because the bulk field theory to a d-dimensional manifold assigns a Hilbert space, and the relative field theory is just taking values in that Hilbert space. Okay, so this is what it means. It's realized as the boundary of a bulk. No? In this construction, the bulk is a topological field theory. No? So it's only sensitive to the topology here. And we realize the theory that we want by extending this d-dimensional manifold along an interval, which is finite, exploiting the fact that this theory has a gapped boundary condition on the other side of the interval. No? So since this is a gapped boundary condition, that means that it is also topological, and we can freely move it along the interval. In particular, we can close it against this relative field theory, and by this operation, we define this isomorphism. This is just the isomorphism is dictated by the fact that I can take this and smash it against the boundary, no? Like literally like this, no? And obtain a definite quantum field theory here, no? So in a sense, this boundary condition is essentially a way of choosing a component of the partition vector of this relative field theory. Okay? Now, why is this useful at all? No? So the idea is that we are interested in characterizing the topological defects of this quantum field theory. These are operators that are topological and that we can move freely around in this d-dimensional manifold. No? Now, like these topological defects have their images in the bulk of the TQFT. And the one that will belong to the spectrum of topological defect of the theory in d dimensions are the ones that are not annihilated by this boundary. No? There are defects that this boundary can just trivialize. No? They trivialize on the boundary. If they don't trivialize, they survive in this theory. Okay? Moreover, if you have a charged operator here, which is charged with respect to this topological defect, that is represented by a topological defect in the symmetry TFT that we can stretch from one side to the other. No? And the charge of this operator will be computed by the structure of the linking of this defect with the other one. In particular, one should really use the linking on the boundary. In the picture that I used is good for abelian symmetries, but on the boundary there is room for making them non-abelian. So this is related to the idea that this topological TQFT is called a Drinfeld center for the symmetry category, but I promised I wouldn't go into that, so I won't. So there is this schematic picture, okay, for these defects. Now, how do we build the duality defects? No? Duality defects, as we discussed, are associated to interfaces, no? between different theories here. No? So a way of building them is to use the fact that this TQFT in d+1 dimension can have zero-form symmetries. Let's call the group of zero-form symmetry of this theory G0. No? So if this one has a zero-form symmetry, remember, is a codimension 1 topological defect. So for the sake of color, let's use the green for this. Okay. So in this picture, inserting for a given element here, we have codimension 1 topological defects, dg. No? And we can consider like just inserting them here. No? It's a symmetry of of the topological theory, we can insert it. No? Now you see, this topological defect, since we are in a bulk boundary system, it can act on the boundary. No? So dg of the boundary, the reference boundary that we use, can become a different boundary. No? So we see that the zero form symmetry of the sim TFT becomes a map between different theories. No? It maps this theory into another one. Now, if this zero form symmetry defect has a boundary, so if we can end it, we can end it along a smaller defect. So this one is codimension 1. This one is codimension 2. No? If that happens, when we perform this isomorphism, no? Maybe the drawing is becoming complicated. Maybe I can redo it. Along the isomorphism, what happens? So here is our defect. Here is the boundary. No? When we perform the isomorphism, here is our relative theory, and here is our boundary B. What we obtain, no, is an interface between the theory TB and the theory T of B prime. No? So whenever we have a zero form symmetry for the TQFT in the bulk that has a gapped boundary, we can obtain an interface between two different theories, exploiting the symmetry TFT. If, moreover, no, this symmetry preserves the relative theory, then we can use this isomorphism to induce an isomorphism here. And in this way, we have streamlined the construction of non-invertible duality defects labeled by this zero form symmetry. So they are just the composition of the boundary with this isomorphism. Okay? Sorry, the choice of patriotic colors is not intended. I just realized. So now, exploiting the symmetry TFT, however, we can consider what happens for symmetry-preserving RG flows. So remember, we have this idea in mind. We have this TUV has to go to a TIR, no? But now, if the RG flow is symmetry-preserving, we can view this exploiting our isomorphisms. So we have this one will be our T hat UV, no? This is the reference boundary. This is the symmetry TFT, and we want to flow. And when we flow, you see the topological part of the symmetry, since the flow is symmetry preserving, is preserved. But what changes is the boundary. No? So in particular, if this theory is gapped, then this must be also a topological boundary condition. Okay. And in particular, if this theory is trivially gapped, meaning that the ground state is one-dimensional and symmetry-preserving, then this corresponds to the fact that there is a gapped topological boundary condition, let's call it BG0, such that it can absorb the action of the symmetry. No? So we can, for instance, study this question in general just by studying whether this kind of boundary conditions exist for this topological theory or not. And this is a very well-posed mathematical question, oftentimes. One can also, like, well, in this case, well, it is trivially gapped, provided there is no topological defect that is condensed by this, along this surface. So you remember, if I have a topological defect that extends here, then there is a non-trivial intersection in this infrared, and that corresponds to the fact that there are some lines that survive. No? If it is trivially gapped, that is ruled out. No? Of course, you can have that condition, and in that case, this intersection will be non-trivial, and in this case, we will have a topological order, a non-trivial topological order, which is again symmetry preserving, but instead of being trivial, has still some structure. It can still match some anomaly. No? However, well, there is also another question. What happens if you have a spontaneous symmetry breaking? In that case, the boundary here is no longer irreducible. So you preserve the symmetry, but the boundary splits. No? And what is preserved is the orbit of boundary condition, and each boundary in the orbit becomes a label for a given vacuum. No? However, the question of symmetry preserving is much more complicated because symmetry breaking is much more complicated, because in order to exhibit symmetry breaking, you need to exhibit an order parameter. And that's a question about the dynamics of the theory. It's not just about the structure of this gapped interfaces. That's more complicated. No? So, well, this is very general. No? What I discussed is essentially a framework. This framework is also related to anomalies. I mean, the existence of this symmetry-preserving gapped boundaries is essentially one of the necessary conditions for the theory to be not anomalous. But that condition can be enriched exploiting some further tools that I won't discuss. For us, since we are interested in this 3+1 dimensional case, we can gain some more mileage. No? So if D is 3+1 dimension, can gain some more mileage. Out of the mathematics of TQFT. So the point is that D equal to 4 is some sort of a critical dimension for TQFTs. TQFTs in D less than or equal than 4 are very interesting, are rich. They have a lot of structure. But for D strictly greater than 4, they stabilize. So somehow they become boring. Okay? And like this distinction is something that can become very powerful when we start considering applications of this machinery to the dynamics. No? Because the fact that these are boring means that the dynamics in 4 dimensions, on the boundary in 4 dimensions, simplifies. There is less stuff to be studied. And in fact, there is a very interesting remark, that was done by you and Theo Johnson-Fried. This is again a recent result, more or less 2021. No? And they say essentially, if you consider 2 field theories in this space of quantum field theories in 5 dimensions, and we say that they are equivalent, if and only if there is a topological interface between them. Okay? So we consider the space of all possible 5-dimensional TQFTs, and we say that 2 of them are equivalent if they can be separated by an interface, a topological interface. No? And you see, like, we are in 5 dimensions. And we are interested in cases where the quantum field theory F is irreducible, no? So in 5 dimensions, topological operators, what we can have? We can have operators that are 0-dimensional. They will be points. We have 1-dimensional. Will be lines. We have 2-dimensional surfaces, 3-dimensional, 4-dimensional. No? But notice one thing, no? So these are topological points. If you have topological points in a TQFT, the TQFT breaks down. It breaks into universes. It splits into pieces that cannot talk to each other, because just inserting a topological point can distinguish between correlators in one and correlators in the other. You can build projectors. And so if F is irreducible, then you rule out the topological points. No? But now remember that if you gauge a symmetry of given dimension, you get a dual one. These ones are dual in 5 dimensions. So if you rule out the points, you rule out also these guys. No? Now, 1-dimensional lines by a similar token are dual in 5 dimensions to the 3-dimensional ones. And the key result by you and Johnson-Fried is that the 1-dimensional lines can always be condensed, can condense. No? So condensation is a mathematical term for what we would call a Higher gauging, or gauging. This is a topological field theory. All these symmetries are finite. We can consider gauging them. And the fact that we can condense them means that we can gauge them on any surface of any codimension. So in particular, we can gauge them on half of space-time. No? So consider your theory in 5 dimensions, take another one, and we decide that we gauge away all the lines on this side. This gives rise to a topological interface between on one side you have the lines, on the other you don't. And so, thanks to this result by you and Johnson-Fried, also these ones are automatically encoded, and one can just restrict to theories that are abelian gauge theories with surface operators. No? These are abelian two-form gauge theories. Yes?
Do they have some we're going to look at some semi-simple things here, or is it valid for generally?
Oh, everything is finite.
Or
no, everything is finite. Yes, everything is as nice as it gets. No, yeah. we are looking at the most simple possible gadgets. That's why we can say so. Yeah. No, because the setup is that of Kramers-Vanier duality, no, and those are always associated to finite groups. No, if we want to study chiral symmetry, that's a different planet. And
also their statements are proven
for finite and semi-simple. Yes. So and I think like in this context we're even assuming bosonic. Yeah. So it's even like. Okay. So if you include fermionic, then 4 becomes tricky, and otherwise. Yes. Well, we can discuss afterwards about this. But the bosonic theories are all gauge theories. Yes. But in this case, you see, like they are all gauge theories of 2 forms, so it's even easier, no? And so, in this context, then it makes sense to study these questions systematically, no? And this is what we do in the paper with Elias and Aziz, no? We can study this. Because we know that we have a good model, no? A good model for all possible SymTFT of all possible 4-dimensional theories, no? And so what are the results? Let's see if I have. Yes, I still have 4 minutes. No, we started in time. So the most general gauge theory will have a structure which is like a sum, if you like, over primes, where for a given primes here we encode a possible prime decomposition. So it should be something that is labeled by p, I, some other integers and ranks. And each of these factors, this one is like a finite d p to the ki to the ri gauge theory. Now, if you have a theory of this form, no, for each of these factors, you can build some zero form symmetries that are subgroups of this. Zero form symmetries are encoded in subgroups of this, where R is the sum of all ranks that appear in the decomposition. No? And here it is crucial to stress that we are not restricting ourselves to the finite subgroups, but we can also have infinite subgroups that become finite once we reduce mod p, or mod p to the k. No? So the problem of classifying the possible examples of Kramers-Vanier-like duality defects arise from the structure of these subgroups, and the possible gapped boundary conditions are determined by the study of the action of these subgroups, action on the boundary conditions. But now you see, since you have this nice description in terms of abelian finite gauge theories, abelian finite gauge theories have an algebra of topological defects are organized by some sort of Heisenberg algebra. So you have operators associated to surfaces and no, that anti-commute according to the linking pairing of these surfaces. And this just follows from quantizing the BF theory and using the line operators that you find by using these discrete gauge fields. So the study of gapped boundary conditions in these cases are just given by the Stone-von-Neumann theorem. They are determined by studying the maximal isotropic Lagrangian sublattices of these for given p and n. And in particular, one exploiting some tricks in number theory, well, in fact, Galois theory, one can, for instance, classify the symmetry-preserving boundary conditions. In general, you tell me your favorite integer, you tell me your favorite five-dimensional theory, we run an algorithm, and we end up with the possible symmetry-preserving boundary conditions, as well as finding that for various choices, there are obstructions to their existence. So for cases where there are no there are no gapped boundaries, one can already infer something about the dynamics, no? Because if there are no symmetry preserving gapped boundaries, then this implies that the symmetry is the duality symmetry is either spontaneously broken or that you are in presence of a gapless infrared. No? So combining that result with the known structure of symmetries, for instance, in classes theories, one can generalize the results obtained in the context of the deformation from n equal to 4 to n equal to 1 star to class S. And as applications, for instance, we find class S theories with lower supersymmetry that exhibits KW-like symmetries, as well as studying the possible, for n equal to 0 deformations, can also study the possible patterns of spontaneous symmetry breaking. In particular, we can reproduce the results from n equal to 4 to n equal to 1 star, exploiting this perspective. Okay, I think that I'm out of time. Yes. No, I think I said everything. Well, I will spare you some tables, but you can find them in the paper. Thank you.
So usually, if I just think about zero-form symmetries, the constraints in the IR come from anomalies, not the symmetries themselves. And it wasn't clear to me whether you were saying the same thing here about the non-invertible symmetries or not. So there's some notion of anomaly which makes sense, and it's the anomaly for the non-invertible symmetry which constrains the TQFT, if it's a TQFT.
This is a good question, no? Because like anomalies anomalies can have different type of manifestations, and like for ordinary symmetries they are all equivalent, no? So an example like of a definition, a working definition for an anomaly would be an obstruction to gauge a given symmetry. Another example of a working definition of an anomaly would be an obstruction to have a trivially gapped symmetry preserving phase, no? So the trivially gapped symmetry preserving phase is exactly the things that we are studying here. However, we are not studying all possibilities, because it is on top of the one that we classify, it is possible to stack them with SPTs, and in that way, like, save the day, cancel the anomaly anyways, no? So what we do in this work is just studying. So you see, in order to use this trick and stack with SPTs and study the anomaly problem, so we rule that out a priori. It doesn't exist. So there is no trivially, there will not be a trivially symmetry preserving infrared for that model. No, there will not be a topological order that realizes that symmetry, because that would require one invariant Lagrangian, and exploiting these tricks in number theory, you can literally exclude them. They are not consistent. And then what you are left are just the two other possibilities. You can either have a gapless infrared or a symmetry which is spontaneously broken. No? Studying the problem of whether this happens or not, that's a problem about the dynamics. So it's related to the existence of an order parameter that takes a non-zero VEV. No? In some cases, like this class Sn equal to 1 cases, we can use other results from holography to argue that in those cases there are no charged operators that pick webs along the RG flow, and then we know that we end up in an SCFT which must have the symmetry. So we conclude that there are non-invertible KW-like symmetries for n equal to 1 class S models out of this. No? However, in other cases, for instance, the example studied by Argurio, Sergio, and Francesco, Christian, and others, and Luigi, so it's a bunch of Italians. But so in this example, they very, very cleverly found an order parameter, thanks to the fact that the non-invertible symmetries in that context mixes with a subgroup of the R symmetry. It's a chiral rotation after all, no? And thanks to that, they can identify the order parameters that takes the VEV that distinguishes between the various gapped vacua, no? And so in that context, they could argue for the spontaneous symmetry breaking, and from our perspective, we use their analysis to argue that the order parameter exists, but then we match the result exploiting the symmetry TFT approach. So we find a boundary condition that splits into components, and computing its overlap with the reference boundary, we reproduce exactly the behavior of the vacua that we expect. So there is a confining vacuum, a vacuum which is Higgsed, they form a doublet with respect to the non-invertible symmetry, and this is all realized using the symmetry TFT. No, so it's some sort of a complementary approach, if you like, and of course it was also inspired a lot by this work on anomalies, no, like. We wouldn't have started thinking about the existence or non-existence of symmetry-preserving gapped boundary conditions if it wasn't for their relation with anomalies, thanks to the works that you are mentioning. Thank you.
Maybe one last quick question.
Thank you.